In video 1, we covered page 2 and the top of page 3 in the note set, and had another couple of important conversations on whiteboards. So this time I'm going to actually start the timer because our goal is 30-minute lectures, because much longer than that, and they take a day and a half for YouTube to load them. Like, well, it'll be an hour and a half, but then like the screensaver comes on, and then like it hasn't done anything. So, okay, so we are here, and we are in the note set, page 3. Right there is where I have my post-it note. So it's all about the post-it notes. True story. So a labeled line, and this is not the slide that talks about labeled lines, so here we are. A labeled line, fill in the blank, labeled line, is the link between the sensory receptor and cortical neuron. So basically it's the literal which axons is the information traveling on. Which axon is the information traveling up. So the modality is the type of stimulus. There are a number of modalities: taste, touch, temperature, pressure, vibration, sight, hearing, all of those. And sensory coding, let's see, I'm not sure if you can see my pointer, so let's turn it to a laser pointer. Sensory coding refers to the codes for various sensory stimuli. Strength, duration, or variation of sensory stimuli. So each neuron can send different messages up the axon by making a different pattern of action potentials. Either more action potentials, more often, duration lasts longer, variation. Anyway, there's all kinds of codings and different ways to send information, which is really cool. So, all right, next. Tonic receptors is that next in our note set. Receptors that are always active are called tonic receptors, such as pain receptors, and nociceptor is the technical term for pain receptor. And remember, C with an E, I, or a Y after it says, so this is 2 C's in a row that says nociceptor. I did cover that in the first video, right? That wasn't one of the videos that I had to delete because I forgot the audio. I'm going to assume we covered that. Receptors that only become active when conditions change are called phasic receptors. So tonic receptors are always active. Phasic receptors really only monitor changes. And our example here is thermoreceptors. Thermometer measures temperature, so does a thermoreceptor. A reduction in sensitivity, change the page, there we go. A reduction in sensitivity is called an adaptation. So all adaptations are reductions in sensitivity. An increase in sensitivity will be a facilitation. So there are different adaptations, but they are all reductions in sensitivity. When the receptor activity changes, that is peripheral adaptation, fill in the blank, which is characteristic of phasic or fast adapting receptors. Our example is the thermoreceptors. They adapt quickly. Put your hands in really, really hot soapy water to wash dishes, and after a while it doesn't seem so hot. Of course, after very long it's not as hot, but when receptor activity changes, we said that tonic receptors that show little peripheral adaptation are called slow adapting receptors, such as pain receptors, nociceptors. And inhibition along a sensory pathway is called central adaptation. So peripheral adaptation happens in the PNS, central adaptation happens in the CNS, hence the words. The CNS, as a reminder, is the brain and spinal cord. And the reticular activating system helps focus our attention. If we focus attention on the pain because we're trying to find it, then we'll become more aware of it. Some pains are small enough that you can ignore them, and they sort of go away. Turning the page to Noteset, page 4. Oops. There we go, page 4. So we have a chart. Ta-da! We have a chart. Okay, you can pause this now and fill that in if you haven't already. But we have two different charts on page 4. One classifies these sensory receptors based on the location of the stimulus, and the next chart will classify according to the type of stimulus. So this, according to the location of the stimulus, we have exteroceptor, proprioceptor, and interoceptor. So the exteroceptors monitor your external environment. This will include most of the general senses, touch, temperature, pressure, vibration, yada, yada. Proprioceptors monitor the position of skeletal muscles and joints. The exteroceptors and the proprioceptors together are your somatic sensory. The slow blink means I'm giving you a second to, process that in your head and, maybe write it down. Interoceptors monitor the internal environment, your visceral organs and their functions, hungry, thirsty, gotta pee, horny, yada, yada. That's all interoceptors, and that is your visceral sensory. Next slide. So type of stimulus. So we're classifying the same receptors, but instead of location, by the type. So nociceptors monitor pain, thermoreceptors monitor temperature, mechanoreceptors measure physical distortion of the cell membrane, and chemoreceptors monitor chemical concentrations. So let's break those down. Oh, we had a question here. What percentage of sensory input are we aware of? 1%. 1% of sensation becomes perception. A very small percentage. Locations with lots of nociceptors include skin, the synovial capsules, the periostea, and the blood vessel walls. As a quick reminder, which you may or may not need, synovial capsules surround each of the synovial membranes, so these will be your joints. And the periostea is the plural of periosteum, and the periostea are the fibrous connective tissue that surround the bones. Peri, P-E-R-I, means around, and osteo means bone, so it's around the bone. And locations with few nociceptors, that'll include the visceral organs and other deep tissues. Nociceptors are free nerve endings, and here's a picture of what the free nerve endings in the skin look like. They're just nerve endings in between the cells. In the cells? Nociceptors are sensitive to temperature, mechanical, and chemical extremes. Temperature extremes, mechanical damage, and dissolved chemicals. Prickling pain, or fast pain, is carried on, well, it's fast, so would you expect it to be on myelinated or unmyelinated fibers? Myelinated, of course, because they use saltatory conduction, which is much faster. And these are going to be type A fibers. Aching pain or slow or burning pain is carried on, well, it's slow, so it's on unmyelinated axons using continuous propagation, type C fibers. Pain receptors are tonic receptors. That means there's no significant peripheral adaptation. As long as there is tissue damage, it's gonna hurt. Now, there is some small amount of central adaptation, which I alluded to earlier, like for headaches, I get headaches. And the little headaches, you just ignore them and they cease to exist, more or less. But then there's like migraines or like real headaches where like you can pretend to ignore it all you want, but it's not going nowhere. So, so there is some amount of central adaptation. And remember, there's two different genes for pain tolerance. You can have one or the other, or neither, or both. So pain is a very individual sensation, and something that might not hurt you at all might really hurt someone else. So, um, as healthcare providers, we're always sensitive to the pain of the people around us. Because pain sucks. So, um, there was somewhere else, something else I wanted to say with that. Okay. If I remember it later, I'll tell you. Uh, Referred pain versus phantom limb pain. I think I have a slide for that. Let's see. Ta-da! So referred pain is when visceral pain is misinterpreted as somatic pain because of the common neuronal pools in the pathway. And because we don't get a lot of visceral pain, the body says, yeah, that's probably the body hurting, because usually the body hurts and not the organs. So this is most familiar to us in the case of heart attack in men, causing left chest pain and left arm pain. Here's liver, gallbladder, stomach, small intestine, appendix, colon, and the ureters. Uh, as a reminder, women's heart attacks don't usually present with the left chest pain and the left arm pain. Women's heart attacks present differently, sometimes left jaw pain, sometimes the left chest and left arm pain, sometimes it's just a complete and utter fatigue, um, which sometimes we're kind of used to anyway. But like then when you're out of breath, then you dial 911 and you tell them where you are. And if you can, you unlock the door and lay down in front of the door. I mean, not where it would hit you, but close to the door where they can find you. So, part of the problem with women's heart attacks are deadlier per occurrence than men's. Partly because men's heart attacks are so familiar to us, that left chest pain, and the guy falls down, and he's fine when he lays down, he stands up, it gets worse again. And women's heart attacks present differently enough, and it's not shown in media all that much. Women having heart attacks on TV is not really something you see all that much, and so we're just less familiar with it. And so women, when they have heart attacks, take longer to call 911. And then when they get to the hospital, it takes longer to get a diagnosis and treatment. So outcomes for women's heart attacks are not nearly as excellent as men's heart attacks. We've done so much with men's heart attacks, and it's so much better now than it was, 20 years ago. So next project. Okay. All right, so that was referred pain. Phantom limb pain is when an amputated limb still hurts. And the reason that happens is because the rest of the pathway, that labeled line, is still there. And it can be activated by the nerves around it. So you can hurt in a limb that's not even there anymore. So some of the treatments, and you see this in all the medical shows, like House, where he kidnapped his neighbor. Don't kidnap people. That's not medical care. That show's so weird. He's so sexist. And where you put a mirror so you can see, make it look like both fists are still there, and then clench the fist you have, and then imagine clenching the fist that you don't have, and that helps. Some kind of weird trick that helps. Another thing that they say helps is after losing a limb, to wear the prosthetic early and often. That the sensory stimulation at the stump helps decrease the phantom limb pain that you will have over time. So, as in so many things in healthcare, you're trading a temporary pain now for a longer term, bigger pain later, hopefully. Worth a try. Okay, now we're turning to page 5. Flip. Thermoreceptors monitor temperature. Thermoreceptors are also free nerve endings, and they are located in the dermis, the skeletal muscles, the liver, and the hypothalamus. So you actually have thermoreceptors in your brain. Weird, right? Oh, yeah, it's the same day as the first video, but I changed clothes because I have this whole wardrobe of work clothes, and it's the COVID times, so I haven't been able to wear them anywhere, and so I'm wearing them now. All right, so the cold receptors are 3 to 4 times more numerous than warm receptors because, evolutionarily speaking, cold is more likely to kill you than warm. So, thermoreceptors are phasic receptors, meaning that they adapt quickly and they really only monitor changes. Next, mechanoreceptors are sensitive to stimuli that distort the plasma membrane. We have here in the side, if you can see it, a mechanoreceptor, which is normally closed. That's what the first picture looks like. And then when you apply pressure to one side, you bend that cell membrane and open that ion channel. These ions are rushing in. This must be sodium and depolarizing the inside of the cell. Let's see. So they are mechanically gated, meaning you just physically have to push to open them. And they are sensitive to, where are we? They respond to stretching, compression, and twisting. Now, there are 3 classes of mechanoreceptors. First are the tactile receptors. There are 6 different types of tactile receptors. They're very interesting. We are only doing the 2 that we're learning for lab. So first are the lamellar corpuscles, and the lab term still calls them lamellated corpuscles. The previous name for them was Pacinian corpuscles. And they are in the deep dermis and monitor deep pressure. As you can see, it's a sensory structure with onion-like layers of connective tissue around it. And being in the deep dermis, you have to really get a deep pressure to activate those deep in the dermis. Now, these tactile corpuscles, which used to be called Meissner's corpuscles, are in the dermal papilla close to the surface of the skin. They do fine touch and pressure. You just barely have to touch to activate those, to just squish them, just enough to open those mechanically gated ion channels. So touch is all about mechanically gated ion channels. So that's why. So that was tactile receptors. Now the other 2 are baroreceptors and proprioceptors, which we've talked about. The baroreceptors, we have it. A barometer measures pressure, as does a baroreceptors. This picture has the rundown of where you find baroreceptors in the body. You should probably read that. And they monitor pressure changes. And that's especially important in cardiovascular, in the arteries, in the respiratory tract, the digestive tract, and the urinary tract. So most of the tracts in the body. And then proprioceptors, of course, are these muscle spindles that measure stretch. And that tells you they're in your muscles and your tendons, and they tell you where your body is in space. And that's how, when you're not inebriated, you can close your eyes and touch your nose. Although the real test with those inebriation tests is that they give you like 3 or 4 orders in a row. And when you're drunk, it's hard to remember all of them. So if you're drunk, you shouldn't be driving because that's stupid. Like, if you want to drink and put your own like health and body and wallet at risk, I mean, that's your choice. But putting other lives at risk for your Convenience is not a choice you get to make. Can you catch that we're talking about masks yet? Okay. This is not a political class. This is a science class. And I'm here to tell you that the science says wear a mask. Anyone who says differently is selling something, to quote the Princess Bride. Okay, so proprioceptors monitor the body position. We already said all that. Okay, so those were the three types of mechanoreceptors: tactile and baro and proprioceptors. So this is not a mechanoreceptor. This is different. This is chemoreceptors. And the chemoreceptors, bottom of page 5, chemoreceptors. And they monitor chemicals. They're okay. They monitor changes in chemical composition of interstitial fluid, which is the extracellular fluid, plasma, which is the fluid portion of the blood, and CSF, which is the fluid in the ventricles and subarachnoid space and central canal. The chemoreceptors adapt within seconds. It informs ANS control of respiratory and cardiovascular function, but does not reach conscious perception. So you're not aware of these, but your body responds to them. And carotid bodies and aortic bodies monitor pH, carbon dioxide, and oxygen levels in the arterial blood. Of those, the carbon dioxide is most important in deciding when you need to breathe. So, where are we on time? I put a timer on, right? Oh, I got like 8 minutes left. Okay. In that case, we're going to start chapter 17. So we're on the top of page 6, chapter 17, the special senses. Page 6. Can you see the 6? Okay. I decided not to use the words at the bottom things, the subtitles, because I couldn't edit them and they weren't spectacular. So, moving on. That's why those aren't there. Chapter 17. Excellent. Ooh, okay. So we're going to do a quick rundown of embryology, which is not on your test, but I feel helps explain where the tissues came from. When I was in school, my first trimester, we had trimesters, we went year round, and so we had 3 trimesters, and then we had finals 3 times a year, and then a 2-week break, and then went right back at it. So it actually worked out really well. But our first trimester, we had embryology, and it was after undergrad, of course. And so my whole understanding of anatomy and physiology is based on where are these cells from. And the whole thing about embryology is the cells divide, they multiply, and they migrate. Okay, so here's the basic concepts that you need to know. We're going to use as few terms as possible because the end of the semester for lecture test 6, we will come back and learn all of these terms. And at that time, I will test the heck out of all of this. But for now, I'm giving you the basic concepts so that they can settle in your brain. And also so that you can know where these cells come from. They don't just magically appear out of nowhere. I mean, there is magic, but magic is only the science that we haven't figured out yet. It's a mystery. Okay, so fertilization, you start with the sperm donor makes a sperm and the egg donor makes an egg. And hopefully they will earn the terms mom and dad. But if not, they still donate their genetics. So the pronucleus from the sperm and the pronucleus from the egg join. There's terms for all of this. And that makes a zygote. A zygote is the single-celled organism that you were. And then you divided and divided and divided. And you were a solid ball of cells. There's a term for that too. And then you made a hollow ball of cells. But you see the three layers, this outer layer is extra cells that'll make the yolk sac and the amnion. And this inner cells, see these inner cells, the yellow and the blue? That's you. And then you made another bubble and you became two layers of cells called the inner mast cells. And this is a cross section through it, but if you see down, it's like an oval disc. And then there's like a little crack down the middle of the disc, and you form, there's a term for that too, we'll get there, this middle layer. So you were these primary germ layers, G-E-R-M, like germs, and because they're germinative, they're stem cells. The ectoderm, the mesoderm, and the endoderm. So the ectoderm forms all of your neural tissue. The mesoderm forms your connective and muscle tissues, and all three layers make your epithelia and glands. So that's where your four tissue types come from. And then they do this. So since we're talking about special senses, here's vision. So that thing on the side of your head was an early eyeball. That's what your eyeballs look like. There's your ear. And these little lumps here are your pharyngeal arches. So one's your maxilla, your mandible, and your hyoid. Now, if you had been a fish, those would be your gills, but of course you're not a fish, so that's like your face. And then you can see this purple stuff is the nerve stuff. The pink stuff is connective tissue and muscles, and the blue stuff is the epithelium lining the outside. So you can see how the nerve stuff grows out and then makes this cup that becomes the retina. So that's where the nerves in your eyeball come from. And then this epithelium bulbs off here and makes the lens. And then there's your palpebral conjunctiva, your ocular conjunctiva. If you don't know those terms yet, then watch the lab videos. Ooh, I wonder if I can make a link here in the video. We're in video 2. Link to lab videos, or at least the playlist. Okay. You can add like cards, but I'm like new to the YouTubeverse. So we'll see what happens. Okay, so then here's your nose. See, you look like a manatee. And your nose, your nostrils start out way over here, and then they migrate in, just like your eyes start out here like a chicken, and then they migrate in. At 5 weeks, you look not remotely human. At 10 weeks, you look like an alien. And then everything migrates in to become face-shaped, except in the case of like fetal alcohol syndrome, where if mama is drinking too much during this first trimester where the face shape is set, then that hinders the migration of the facial structures in. So if you Google fetal alcohol syndrome, you can see that mama's alcohol problem shows up on baby's face for the rest of their life. So don't drink or do drugs while you're pregnant. In fact, papa drinking on the night of conception decreases baby's IQ. So nobody drinks when you're trying to make a baby. Although in more unfairness, we haven't, it's the beginning of the semester, we haven't covered much unfairness. So in our first instance of complete and utter unfairness, because people with ovaries are born with all the eggs they'll ever have, all the alcohol and drugs you ever do can damage the eggs. But people with testes make new sperm like every 90 days, and so they can just quit drinking and make healthier sperm again. Not fair. Not fair. I mean, drugs and alcohol are bad for you anyway, so. and would keep you from getting your health provider license, be it nursing or OTA or PTA, whatever it is you're going for. Anything that would keep you from getting or would make you lose your career that you're working so hard for is not worth doing. Okay, so gustation is taste, and these are the little sensory neurons, and wherever they hit the epithelium, they create these taste buds. So if you cut this and it grows back somewhere else, they'll grow taste buds there. Neat, right? Okay, so olfaction, top of page 6, smell. Oh, there's our timer. Okay, that was a very nice timer. I like that one. Okay, so we will start back here at the top of page 6. Let me put the page number on the post-it. That's not the right post-it. Okay, how about I do my outro and then search for the post-it? Oh, it's in the notes. That's why. Okay. All right, so thank you, as always, for listening in or tuning in. I did audio lectures last time. We're doing video lectures this time. So this has been video lecture for AMP2, lecture test 1, video 2, poop, now I gotta find it, video 3, video 2. We started at the top of page 3 and we got through page 5. Okay, video 2, note sets, page 3 through 5. Thank you again for listening in, tuning in. Sorry, not an audio. This one's a video. So thank you again for tuning in. The education must go on. Dr. J out. Oh, now I have to get everything off the keyboard so that I can Command, Control, Escape. Have a good one.